stay with us here also in the second part of the SPARQL Endpoints and Web API tutorial. So in this second part, we'll be focusing more on not necessarily on the backend, but if in Pasquale's part we saw how to fine-tune knowledge graph access responses, right, to suit our needs. In this second part, we'll see how to we'll look more closer into how we make those requests to knowledge graphs. So we'll basically do this in two parts. So first, I'll be talking a little bit about web APIs for RDF, and in particular, web APIs for on top of SPARQL endpoints. And then we'll look into grlc, what grlc does, and what's the gap it's supposed to cover, the specific problems it's addressing. And I'll give you a very, very quick walkthrough on how to use it. There are many different ways to use it. We'll just do something very similar to what Pasquale did. I'll show you a place on the web where you can just use it online. You won't need to install anything on your laptops to get a grip of how it works. All right then, so web APIs for RDF. So if we look at how we usually query knowledge graphs in RDF, here you see an example in SPARQL. You know, that's not necessarily a requirement. We could be doing it in GraphQL, as Pasquale showed before. There are many other choices, but let's just suppose that this is the typical scenario where a developer, in this case, the data scientist, the one you see in the left-hand side of the screen, wants to retrieve some data from a knowledge graph over HTTP. So the basic plan is on basically typing a query, just crafting this query that retrieves works that are of a certain type, that lie in a certain museum, and that have a certain name, certain images. We don't want more than 100 of them. And then we use HTTP to send the SPARQL query over an endpoint, and then we'll get some JSON back to use. And we already saw how we can fine-tune this JSON, and in particular, this JSON shape, and to avoid redundancy of results and everything we saw in the first part of the tutorial. So this is all fine and nice, but this is the typical workflow that we have in place when a human queries a SPARQL endpoint, right? So, or a scientist just manually writes this query. Let's just say to throw it perhaps in the order of the tens of times, right? So typically you don't want to throw this query more than 5, 6, 7 times. So this looks a little bit different when we look at it from the perspective of an application. So what happens if we are a developer and we don't want to repeatedly be writing these queries? We rather want them, you know, some backend or some application to be executing these queries in the order of the tens of thousands or hundreds of thousands of times. Now, this works a little different, right? Because despite using the same query language, in this case, SPARQL, and the same transport protocol, in this case, HTTP, and the same query response language, namely JSON, it is an application that will be throwing this query. So we don't have a scenario anymore where we can just fine-tune this query and be manually hacking it and rewriting it to see, you know, whether it works, whether it doesn't work. We need something that's robust and just capable of being run in the order of the hundreds of thousands of times. And so it needs to be very repetitive or repeatable rather, and highly parameterizable, right? So it's very unusual that the application just will want the first 100 results of works shown in the Louvre, right? Most probably we'll want these applications to show us pieces in other museums, or things that are not necessarily of type DBO work. Or maybe we'll want some other properties rather than just the image and the name of the work, right? So we need some capacity to abstract and parameterize these queries in some sort of way. And typically the way this happens in an application is at the very fine grained level at this point where this HTTP request and this HTTP response happen. So this is a two-way interaction, right? So you'll know that probably most of you will know the ways in which HTTP works, right? So it has these two parts. So first there's the data request, where we sort of prepare the query, just write this query. We have the final form of this query represented in some data type, typically a string. We prepare it, and then we prepare the request parameters, and we send it over HTTP probably to a SPARQL endpoint address. And then the SPARQL endpoint will receive that request, it will process it, it will create some triple store, it will do some very complicated SPARQL query solving and planning and solving, and then it will throw us back a data response. And this is exactly what we saw in the first part of the tutorial, right? So how to fine-tune this query response so that it fits the application model that we are using in our application. All right. So in this second part of the tutorial, we'll be focusing on this data request, right? How does it work? And in particular, whether we are doing it smart enough and making it, as we said in the beginning of the tutorial, easy enough for developers to use in their production grade code. So this is a simple example of how to use how to query using a SPARQL endpoint over HTTP. As you can see, there's nothing in this particular example. There's nothing particularly tied to SPARQL itself. So this is the example in Python, which is just using this library requests that makes very easy to just send HTTP requests over the web. Any other library would work exactly the same. Think of CURL or other similar libraries. Request is just it's a very simple library to follow to send HTTP requests. And everything we actually need to prepare for a SPARQL query to work over HTTP is very simple, right? So we just need to compose a very long URL. That's what we need to do. And that URL starts with the endpoint address, right? Because that's ultimately the place where we're sending the query string. So something like, query.wikidata.org/SPARQL, that's the SPARQL endpoint of Wikidata. And then obviously we need to encode the query in the application code in some way. This is probably the most straightforward way in which we can do it. We just type the query string into a string, or in other languages, it would be a similar data type. And then we prepare that query string as the payload of the request. Now, what this means in very low level terms is that this query string will be URL encoded, right? So there will be some replacements of special characters like blank spaces that cannot happen in a URL. And then everything will be appended at the end of this endpoint URL as probably a parameter, right? So we'll have this /SPARQL and then question mark query equals, and then the URL encoded version of this query. And that's what we'll be sending to the endpoint via a GET request. And once the processing of that request is done, we'll get the response back in probably in this R object. So this is very, very simple, right? And it's exactly the way HTTP works. Now the question is, do we need to do this in this sort of low level, kind of archaic way every time we want to query a knowledge graph? And the answer is obviously no. There are many, many different libraries to do this in a more abstract way. I won't go through all of them because there are just way too many. But just to give you an example of something that's been used over the years in Python, that's SPARQL wrapper. In a way, what we need to supply SPARQL wrapper with is similar to a plain HTTP response. So we need to encode the query in some way, and we need to supply an endpoint HTTP address. And then we just need a way to tell the library to send this query over the endpoint. So no rocket science really. It's just we can continue to build abstraction layers on top of this as we want, but ultimately we need to provide just the query string and the endpoint address in order to be able to send these over HTTP. So this is pretty standard. This is the way developers mostly interact with SPARQL endpoints, typically in backend scenarios, and it's the way we've been doing it since the very early days of the semantic web. But meanwhile, on production environments, and since the early 2000s, a different kind of practice, a different kind of paradigm for querying data on the web was sort of emerging, right? And that's the one of RESTful web APIs. So RESTful web APIs are kind of different, right, to what we just seen in the previous examples. In RESTful APIs, we just have textual representations of web resources via URIs. So we have a specification of an API, for example, as you can see in here, where we have some resources, right? In this case, organizations. And then we have a set of stateless operations. And this is just a very fancy way of saying that to access these resources, we'll be using HTTP verbs or HTTP request methods. And these are the typical get, post, put, delete, update, and all these verbs that come with the HTTP spec, and for which most of the time we're just typically using get and post, but obviously this suggests that we should be using all of them depending on the context. And then what applications do is not to encode a very complex query in their code. What they just do is they look at the spec, and depending on the application flow, they select one of these resources and one of these verbs. And that is everything the application needs to send to the backend in order to get data back. So it's just a different way of accessing web structured data programmatically. And in order for these to be able to happen, as I said before, we need something that was not needed in SPARQL interaction, or it was perhaps needed to a lesser extent, which is an API specification, right? So we need to tell applications, we need to tell developers of those applications what the full list of operations and methods is available, right? And there are different languages for and standards for specifying those operations, but OpenAPI, previously known as the Swagger spec, is typically the way in which you do this. So it's an API description format for REST APIs. It can be encoded in YAML or in JSON, and it just lists all these endpoints and operations. It shows a full list of parameters that are expected as input for these operations, the output these operations are providing, also of any authentication methods for the API, some metadata such as contact, license, terms of use, and whatnot. And what's important to say here is that this is not an actual implementation of the API. All right, so this is just a specification. It's nothing that will make the API work. It's just what the API exposes to the world and to client applications, so that these client applications know what paths are available and under what methods. So as I was saying, the OpenAPI spec can be generally dissected in these three main sections. So There is one for a section about metadata, telling you things such as, what's the title of the API, what's the OpenAPI version of the specification it follows, what's the specific version of this API. Then we have a section for server routes. So these are the base URLs and the resource prefixes that all URLs will start with. We can have more than one. In general, this is useful if we have, for example, a production API and a testing API. And then we have a long section, and this is perhaps the most important one, of so-called paths. And paths are these web resources identified by URLs for which we have different access methods. These are the HTTP verbs. Here we have an example with get. We could have another with post. We could have another with put, along with the parameters and responses that each of these paths expect to work. And as I was saying, this is exactly how one of these paths with a description of its parameters works. So, for example, in the previous example, we could have just a general method called users. This doesn't require any parameters. We just call this path with get. We'll get a list of users, most probably. In this particular example here, a parameter is expected from us. So we need to call a particular user with a user ID. This ID probably we get from a previous request asking for all users. So we get all user IDs. And then there is this required parameter that we need to supply as the URL path in order to get information about this particular ID, this particular user. And then OpenAPI also gives us a way to specify the different types of responses this can get. 200 is okay. We could also have 500 responses in case of error, 400 responses in case of resources not found, 300 responses for authorization errors, and so on and so forth. So in general, two very different paradigms for querying open and structured data on the web. On the one hand, we have querying knowledge graphs, which are good because they offer just a myriad of different methods, right? We've seen SPARQL, but there is something called linked data fragments, which uses a different API. We have dumps, we have RDFA. So in general, we need lots of different libraries to support these linked data and knowledge graph specification technologies. They are not very widespread among developers. There are some developers in this community that are obviously that won't obviously agree with this statement, but out in the open, SPARQL and RDF are not super known by developer communities. A very good thing that these languages provide is high language expressivity, right? They give a lot of power to the developer to compose these complex queries and ask exactly for the data he or she are interested in. But on the other hand, the query stability is very low, right? So it's very hard to guess for how long these queries will be valid. It's very hard to guess to what extent these queries will be too complex to deal with by the endpoint. There is also this complexity issue here. That's in general a disadvantage when using these query languages from application code. On the other hand, this sort of materializes to the other side of the spectrum in using APIs, as I just mentioned. So we only have one access method. It's the OpenAPI specification or any REST API compatible specification. It's very simple. Usually one library is enough to access it. It's very widespread among developers. On the other hand, language expressivity is very low. There's somebody else controlling for us that in the backend, a specification is given to us, and that's everything we can execute as developers. So that gives away some expressivity power. On the other hand, query stability is very high. So we have a serious spec to be complied with. This spec obviously can change, but in general, it is supposed to be stable over time. And in general, backend developers can control response time to a very high degree. Now, an important question would be, can we have the best of both worlds? So can we have the best of query knowledge graphs with all the nice things that knowledge graph query languages bring to us, and the added value of having REST API specifications on top of that? And the answer is yes. This has been done in a number of projects. OpenFacts is one such project. The idea is to maintain the full stack of RDF and knowledge graph technologies at the bottom, right? So to use the integration power of RDF, linked data, semantic-web, SPARQL, just as it is, but then add an additional layer of abstraction and even security on top of that by providing a REST API layer on top of the SPARQL endpoint, which is the only layer responsible for accessing and using that SPARQL layer, right? And then that REST API is what communicates to the rest of the world, to humans and machines alike. But then it's the one that also translates REST API requests into SPARQL requests. So that's the basic idea, to add this REST API layer on top of SPARQL endpoints. This provides some advantages, and basically it provides us with this abstraction in which every query turns into a service call. So one of these URI resource identifiers that we saw in the API specification. We've already seen in the first part what the limitations of just standard web APIs are. So we've seen that controlling results is hard, and that most of the times we want fine-grained tweaking of the JSON object nesting. That's what we saw in Pasquale's part, in the first part of this tutorial. But there are two issues that remain in this case, even if we add this additional abstraction layer on top of SPARQL. So the first one is repetitive labor, and the second one is query management. And I'll try to argue for each of these. So repetitive labor relates to something that as developers you'll very quickly sympathize with. This thing of writing REST APIs on top of SPARQL seems very interesting. It seems reasonable and nice, but it has to be done. Some developer has to code those APIs, has to write those OpenAPI specifications, and this is just plain very, 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 very boring work. Here you can see just how redundant a backend implementation for such a service would be, in this particular case in Java. And you can see that there's just this extremely verbose method header in which in most of the cases we'll just want to have some kind of hard-written SPARQL query in this part, so in the body of the method, that is just responsible for submitting it to an endpoint and then returning the result to the user. So in general, writing over and over these methods for this kind of knowledge graph APIs is just plain very repetitive and plain very boring and just very, very inefficient. So this is the first problem that we'll be addressing in this second part of the tutorial. The second problem is kind of the elephant in the room. And I think I've shown you a couple of examples already, but in general, what we're doing here, one of the key problems in the maintenance of all this API code and in general application code that access knowledge graph data is how volatile and lowly reusable and badly synchronized these SPARQL queries are if we hard type them in application code. So if we simply have them hard written here, and as I showed in previous examples, the fact that we are just having these SPARQL queries hard typed here in the application code that is supposed to be consuming them. So kind of the elephant in the room is query management. This is just very poor query management. We don't have a stable place where we are storing the queries. We don't have a stable place where we can parameterize these queries, where we can version these queries. We simply just go with this approach of hack and go, and when the query works, we sort of hard type it into the application code, and off we go. So this query management is kind of the elephant in the room that we'll be addressing in this second part with Garlic, as promised. Okay, just a quick view on the time. All right. So what is Garlic? So Garlic is a service that aims at solving these two problems, right? So the problem of repetitively having to specify and code APIs on top of knowledge graph query interfaces, such as SPARQL endpoints, and the problem of poor query management, in general, just hard-typed queries in application code. And it lies on the assumption that a sufficiently well-described query repository contains as much information as a REST API, and actually that the task of creating a REST API on top of a knowledge graph is completely trivial if we are good enough at managing our queries and at richly describing these queries. All right, so that's exactly what Garlic does, addressing these two problems. Now, it does it under certain assumptions, and this is very important because so as you probably can expect, some of these service implementations can be, and probably in a lot of cases should be, more complex than just one single SPARQL query. So some of them simply are more complex than that. So Garlic works under the assumption that one service is implemented in one SPARQL query, and that's it. So that's the first important assumption. And the second important assumption is that there is some external system that is responsible for query management. So as important as I tried to make query management right before I started on describing a solution, here we'll just assume that there is a system that does good query management, and then prove that we can build REST APIs automatically using that query management system. And in particular, this won't be a surprise. What it does is it automatically builds OpenAPI specifications, as we've seen before. It answers API calls, so it doesn't just compose these OpenAPI specifications. It also implements their operationalization using the query contents, of course, and then it manages the parameter mapping and the response mapping between API calls and what we'll see a little bit later in SPARQL variables. All right, I'll have a quick look at the chat to see if there are any questions so far. If I can get that to the screen. Okay, I see there are no questions so far, so that's great. I'll just carry on. There we go. So as I was saying, assumptions, one service is one query, and there is some external system managing our queries. So this is overall how Garlic works. So just try to think of how the situation was before Garlic. Try to think that there is no middle layer in this. That this middle layer doesn't exist. You just have a client application that needs to communicate directly with this myriad of knowledge graphs via HTTP, right? So there would be just these two straight lines between the client application and the knowledge graph access interface, right? So this is typically how this interaction would work, just an HTTP request, an HTTP response, end of the story. And here we're adding two important components. One is, as I was saying, the one that addresses the elephant in the room, Pandora's box, query management, well done. And it's this particular case, as we'll see in the following slides, the query management system that we're using, which is, interestingly enough, not a query management system, properly speaking, is GitHub. But just consider that this could be any query management system we can access via HTTP. And this middleman here that we call Garlic, which is responsible for creating these web API specifications and implementations between client applications and knowledge graph access interfaces. And the way Garlic does this is just it just accesses our query management system. It gets us a big bunch of metadata that we'll need to properly and fully describe our APIs, and creates that OpenAPI specification for us. At the same time, since it has access to the body and just the content of these SPARQL queries, it also composes the HTTP requests that are needed to answer the queries by just executing the queries themselves against the endpoints. So that's the basic idea. Now, GitHub as a query management system. So why are we using GitHub as a query management system? Well, the first and short answer is because we don't know of any other and any better query management system for knowledge graphs. And we are working on, as we speak, on a white paper for coming up with a full list of requirements for a proper query management system for knowledge graphs. But the truth is that we don't have a proper one. And this is the reason behind using GitHub. There are all sorts of secondary reasons, such as in the projects I come from, and in which in the project where we come from, Pasquale and I, we already had this practice of dropping SPARQL queries in separate files in GitHub repos, but that's just sort of the accidental story. But the truth is, GitHub is actually quite good as a query manager. It has good support of query curation. It supports versioning out of the box because of how the way Git works. It supports branching. It supports this clone, pull, push architecture. It supports this sort of collaborative approach to writing SPARQL queries, which was very, very lightly touched in almost 20 years of semantic-web research. And it also gives us very nice web-friendly features, right? So it gives us one URI per query, and it makes these queries identifiable on the web and dereferenceable, right? So via the raw GitHub API, we can interact using HTTP with GitHub and just request the body of these queries, request specific versions of these queries, know who wrote the query, who messed up at writing a query, just as we would do with any other programming language or any other piece of code that's living on GitHub. So take away from this slide, let's just use GitHub for now as this query management system. Of course, this comes with its own set of of important pros and cons, right? And one important limitation is that there are many parameters, many things that we need to fill in the OpenAPI specification that we need to get from somewhere. And fortunately for us, one of the things that Garlic does is to map these properties that we need to write a valid and complete OpenAPI specification from the GitHub API. So things like the API version is something that we can get from the API. The title of the API is something that we can get from the repo name, contact name, content URL, license. These are all things that we can get via the GitHub API, as well as path names and schemes. Now, these are things that are easy to get from the query management system directly, but there are other things that we cannot get from that because they are operation specific. They're specific to the particular call of the API that we want to implement via a SPARQL query. And for that, we're going to need something we call SPARQL decorators. So we'll need to enrich these SPARQL queries with a nice set of what we call query decorators, which provide additional metadata on top of the query, so that Garlic will be able to compose a fully compliant and correct OpenAPI specification. Very good. So this is exactly how this SPARQL decorator syntax works. So we'll have somewhere stored SPARQL query of any kind. Here you can see an example. And then with these SPARQL decorators, what we mean is like these comments on top of a file containing the SPARQL query. So what's nice about this syntax is not that we're particularly fond of YAML or of these and that metadata or specification format. One reason for using this syntax is that we don't pollute the SPARQL syntax. So this query is still valid and SPARQL conformant. We're not breaking the standard by just adding these lines here, these comments on top. But as it happens, this is, if we just get rid of the comment symbol, this is valid YAML syntax that we can retrieve and parse and interpret. So this is what we'll be using in this tutorial. There are other ways that Garlic supports the supply of these additional per operation metadata. We'll just assume, we'll just go with this YAML syntax for now. So this is exactly the way Garlic works and how it maps the behavior of your queries in GitHub or in any other query management system into the OpenAPI specification. So basically, if we just assume that we have a repo with queries this address in GitHub, you can just call these URLs in Garlic. This is the main Garlic server. You can install your own Garlic instance without a problem. But these paths will work in any Garlic installation. So you can just do API get, and then owner /repo, and then /spec, and that will give you the JSON specification. If you don't add the spec drilling, you'll get the OpenAPI with a graphical user interface, what you'll typically give to your users. And then the way parameters are mapped, and we'll see these in the next slide in more detail, is just adding them back to the operation name in calls like this. Now, there are other ways of using Garlic, as I was saying, just because we don't need to assume that GitHub is going to be the only query manager out there. If you have a local query manager, you can just use roots starting with API-local. If you simply assume, and this would be the webby way of doing things, that queries are available on the web, you don't care about what the query management system is, you just know that they can be retrieved via HTTP, there is a way of supplying those SPARQL queries using the API / API URL. But today we'll just focus on using GitHub as a query manager. So parameter mapping. So there is something very important that we need to consider here, which is the way API parameters will be mapped into SPARQL queries. Remember that example in the beginning where, for example, the user's API needed to be supplied with the user ID parameter to know what specific user we wanted to get details of. So the way this parameter mapping works in grlc is very simple. We just we just map HTTP parameters into certain SPARQL variables. So we change in a way, we change the semantics of SPARQL in that way, because variables in SPARQL that start with an underscore, those are supposed to be mapped into HTTP parameters. And what will happen in the internals of grlc is that so we'll pass the value of these variables supplied by HTTP into the place. We'll give value to these SPARQL variables through the values SPARQL clause. So for example, you have a parameter called P1. So it will be mapped into the SPARQL variable underscore P1, and then optionally underscore IRI. So this underscore IRI is there because you can specify a variety of different data types for these parameters. So in particular, you can specify that something is a literal written in English with the underscore N trailing. This can be done with any other language tag. Integer if your literal is an integer. IRI if your parameter is supposed to be a URI or an IRI. And in general, if you just use prefix any data type name, it will be mapped into prefixes of that particular data type. All right. So basically, this is the way in which the grlc service works. So it will send requests to the GitHub API in order to retrieve your queries under your own repo. Suffice to say that if you make your repo private, this won't work unless you supply grlc with your access credentials. So everything will be easier if you just go for public APIs, but there is definitely support for private APIs as well. We'll dereference all queries, all files in that repo that are named whatever .rq or whatever .sparkle. So we'll assume those are the files containing SPARQL queries. Of course, this means that your SPARQL queries can live with other kinds of files in your repo, but we'll only read the ones containing SPARQL. And the nice thing about this is that we can very easily support versioning, right? So if instead of accessing just your API at /owner/repo, if you add /commit/ and then your commit hash, you'll get the API for that specific hash, for that specific version of your repo. All right, so now I'll get through the full list of grlc features. So everything you can add to those query decorators to make your API fully described and fully compliant with the OpenAPI specification. Before I do that, let me have another quick look at the chat, see if there are any questions. Yes, I see a question here. So what is the return type of the API generated through Garlic? Is it configurable like JSON, JSON-LD? Yes, so this is a good question, and I'll get to that in, I think, 3 slides. But yes, you can configure the return type of the API via content negotiation. And then Lionel asks, can we currently change the query management system to another DBMS like CouchDB? Yeah, so the short answer is yes, through this mechanism I mentioned here of using API URL. So this is intended, so we can address this in multiple ways, right? So one way would be building wrappers and connectors for all sorts of query management system vendors, which would be nice, but also expensive. We're just academics. So what we do is to provide this HTTP access layer, right? So if CouchDB has a mechanism, and I don't know this because I haven't used it extensively enough, but if CouchDB exposes queries using HTTP, then you can access those queries and have REST APIs via this API URL mechanism. Then Nai is also asking, can I use Garlic for queries stored in other platforms except for GitHub? Yes, this is sort of a different version of the previous question. Yes, you can. You can have those queries stored locally. You can have those queries exposed. So the main takeaway is that you need those queries accessible, either in your own server, your own machine, or accessible through HTTP. If they're accessible through HTTP, then you can use them in Garlic. And then Miguel is asking, so you don't map the results to JSON or something, right? This is a good question. Garlic per se doesn't do any mapping, and you're already seeing where this is going, right? So everything Garlic does is it does the parameter mapping. It sends the query to the endpoint. It does some. It tries to be compliant with the content negotiation, right? So with the kind of content that the user is asking, but it doesn't manipulate per se the JSON results, right? That's what SPARQL Transformer does. Now, I don't want to spoil the surprise, but there is a nice way of combining the two at the end of this tutorial. But in principle, the short answer is not yet. So yes, but not yet in the tutorial. There you go. All right. All right, so we're a little bit late because I was supposed to start a hands-on 20 past. So we'll do this very, very quickly. There we go. So so this will be just an overview so that you can start the hands-on. These are the kind of things that you can add on top of the SPARQL queries in your query management system, right? So the kind of comments that you can put in YAML on top of the queries. Things like the summary, the endpoint, the name of the method, and the tags. So the name of the method that you'll see in specs, like foo's, for example, that's the name of the .rq file that you put on your GitHub repo, or the name of your .sparkle file. So that will be used as a query name. And then things you can add in there are the summary, so a description of the method, the endpoint, very important. So the SPARQL endpoint against which you want to throw your queries. The HTTP method. Get is what you'll want to use most of the time. We don't have time enough to go into full detail of other methods. But some other HTTP methods are also supported. And then tags. So tags are supposed to give you some sort of nice organization of paths into your API spec. Other things that you can do is to have default values and enumerated parameters. So what happens if you want to give your user a default value for a parameter, because that can be confusing, or you just want to give them some help. You can do that with the defaults keyword, and then have a list of all parameter names without the underscore that you would use in SPARQL, and without the trailing underscore and the data type. So that's the way it works. And then colon, and then the name of the default parameter for the default value for that parameter. That's how we use defaults. And then there is a nice way of doing enumerations. So this is a feature that the OpenAPI provides, so that you can tell users what are the possible values that you can give a parameter. So this you do with enumerate, and it works in exactly the same way. So for every parameter that you want to give an enumeration, you just give a list of all the possible values for that parameter. Another thing you can do is to query multiple knowledge graph querying interfaces. So I've mentioned SPARQL all the time, but you can also query RDF dumps. You can query RDF web pages. You can query link data fragment servers, and have everything behind one unique homogeneous HTTP API. You do that with adding this MIME text / turtle type. Another nice feature is pagination. So pagination is very important for applications consuming structured data, because you certainly don't want a result set of 100,000 results out of your request. So the way Garlic implements pagination is very similar to what GitHub does with its pagination API. Basically, you can add this a SPARQL decorator called pagination 50, and then Garlic takes care of combining limit and offset in your query with a nice set of rel links in the HTTP headers, right? So when you get your response back from the server, you can always get a link to the next page of results, to the previous page of results. So what Garlic call do you need to make to get the next 50 results, for example? And this adds an extra parameter that's sort of, it's not really hidden, but it's always there in every Garlic call called page. So this is sort of a reserved parameter. Don't have a variable called underscore page in your API, which defaults to 1 because you always want the first page if the user doesn't say otherwise. Another interesting thing is that Garlic provides full provenance traces of everything it's done using W3C prof and Git2prof. You can get nice visualizations of provenance trails of telling you how your API was generated. There is no specific Garlic API call for getting those, but you can get the provenance triples if you press the "Oh yeah" button in any OpenAPI spec generated with Garlic. And this is to answer the question that was posted before in the chat. Content negotiation, we currently support CSV, JSON, HTML, and XML, and I believe also JSON LD. So basically, we do this in a kind of agnostic way. So we pass, Garlic passes the content type to the SPARQL endpoint, and then if the SPARQL endpoint supports that return content, which is sort of to be expected if it's a SPARQL compliant endpoint, then it will return the results in using that type and then back to the client. So you can try that just by using curl, for example, outside of your browser and specifying the specific content that you want that you want your response to be in. And finally, there are many different ways to use garlic. We won't go through all of them because it's really a lot. You can install it via pip and use it programmatically from your code in case you want some of these nice features directly in your backend. If it's the backend what you're interested in, if you're just interested in using it from a client, just use any HTTP library to cleanly access knowledge graphs by just issuing web API calls as you would do with any other structured web data supplier on the web. There is a nice Docker image in Docker Hub. You can get it like that. There are many parameters that you can specify either in Docker run or via Docker compose. There is abundant documentation about all of this if you're interested in running your own garlic instance. But of course, the easiest way to use it is just using the public instance is right there in garlic.io. You just need to compose a URL, as I mentioned in the tutorial. There are several examples in garlic.io that you can, for you to see and follow. But in general, the kind of principle is that you just use so this prefix garlic.io/API-get/ and then your username and your repo, and that will create the API on top of your queries. So I'll give you the hints now for the hands-on and give you some time to answer the exercises. Before I do that, I'll have another look at the chat to see if there are any more questions. Okay, I'll take that as a no. So so here are the exercises. It should be all very simple, but I'll be here to help you out if you need help with them. So as I said, everything you will need is to go to garlic.io to try to and try to open the default APIs and pages. If you're interested in the source code or you want to contribute, this is the GitHub repo where Garlic lives. But in general, everything you'll need is to create a GitHub repo. So if you don't have a GitHub username, which I doubt, but in case you don't have it, you can just go and create one for free. And then create a new empty repository, just clone it locally or just edit files up there in the via the GitHub web interface. And the first exercise will be to create an API with just one get method that retrieves all DBpedia bands. So all entities in DBpedia that are of type DBO band. And then you'll need to use the summary and endpoint decorators to get that API running. So just try to create one SPARQL file.rq that contains such a query with the decorators, push it to your repo, and then try to open this web page, garlic.io/API-get/your username/your repo name. And something very important, beware that prefixes in your SPARQL query are mandatory. If you don't add prefixes, Garlic gets very angry and it doesn't, you won't see the operations popping up in the API spec. So add as many prefixes as you need, in particular if you're using DBO in your SPARQL query. And then if you feel brave enough, I won't show you the solution for the first one, try to extend this call so that you have another call so that the DBO band type becomes a parameter called type, so that you can supply that parameter as part of the API. All right, I would say let's have about 10 minutes to play around with it. .rq or .sparkle file in your repo, and then just call your repo from garlic. So very simple. Oh, I see there are some new questions in the chat. Himanshu asks, sorry, we joined a bit late. So if I understand correctly, Garlic will scan the repo for SPARQL files and create endpoints automatically, and SPARQL responses turn as it is without any wrapping. Is that correct? Wondering if it's okay to change the underlying query without affecting the client, which is calling the APIs. So it will scan for SPARQL files. That is true, but it will create. So it will create the if by endpoints you mean API endpoints, yes, that's correct. Not SPARQL endpoints, but API endpoints. The rest is exactly as you say. So the only difference is that the underlying query can change indeed without affecting the client, which is calling the APIs, and that's one of the advantages. That since you give a stable name to this query, you can change the contents of the query as often as you like, without having to change the code in the application that's using that query. That's one of the advantages, rather than a Garlic advantage. That's just one advantage introduced by using a query management system, as I was mentioning before. But yes, you're 100% correct. I say Lionel is also throwing some APIs around there. That's really nice. Miguel is also asking, is there a way to get the pagination value from the API parameters? Not the value, unfortunately. That's a good question. You can get so you can set the pagination value in the query decorators. What you can get what you can use as API parameter is the page number. So you can ask for I don't know, page 35 of results using the parameter page. It always uses the same name, but not the pagination value, unfortunately, because I would mess up with what we're using as standard for using API call names and page names. All right, so this was the answer to the first exercise. The second exercise was asking you to just change this DBO band into a parameter that you could set via an HTTP parameter. And this is how you do it, right? So you can just have exactly the same query as you had before, and all you need to do is to replace the DBO band object by the underscore type variable, and then since you're using the underscore notation, this variable will be understood as a parameter. And then if you want to set a default value for that parameter, for example, using DBO band, you can do as much using the defaults namespace, the defaults option, sorry, the decorator. Okay, so there are two more exercises for you to do, but these are for homework, and they explore the rest of the options that we explained over the tutorial. So before we let you go and that we wrap up the tutorial, and as correctly foreseen by some of you in the questions in the chat, there is something to say about SPARQL Transformer and Garlic together.
Yeah, I take the voice. Yeah, sorry, I wanted really to underline the effort of putting Megazord in slides. That is a thing that we really wanted to do, just to make people know how nerd we are. So, okay, yes, since well, more or less 1 year, we started to integrate SPARQL Transformer inside Garlic. So from now, basically, it's possible for you to use SPARQL queries. So Garlic will search in your repository if there are SPARQL query and analyze them. And as you can see here, well, you can use all the feature of SPARQL Transformer and all the feature of Garlic. So you, in the same time, you deal with the request with Garlic and the response with the SPARQL Transformer. So you can use the var modifier for making parameters following the naming convention of Garlic, so to make them some parameter of the query. The lang is an automatic parameter for your query, so you always have it. And finally, with this Garlic attribute, you can insert all the properties that you normally have in Garlic. You can find a full example with more parameters and so on, and a query a bit more coherent at the URI in the slide. Okay, so this was everything for us from our part. So we take now a bit of time to answer your question, further questions you may have. And actually, we are very welcoming your feedback about this tutorial. I think to speak also for Albert, to say that this was the first time that we do a tutorial completely online, so it was a new environment for us. So it's possible that we failed sometimes in making progress. So we will happy to listen your voices, to collect your feedbacks, and or now or in the chat as you have done, or you ask the voice, you just write hand in the chat and we will let you speak. Or in any case, we will be available. Those are our Twitter handlers. Write us for any question, doubts, anything. We are at disposal to answer your question. Lionel, very nice explanation. Resources provided. Thanks. Thank you, Lionel.
Thank you.
Hello, if I may, thank you very much for the presentation and the workshop. I think it was very interesting, and it's very nice work and inspiring. And I have a question about integration between Garlic and SPARQL Transformers. So you did that like as a library, right? But my question is, if you try to do something like that, like from the Garlic, just a standard for just building everything as a SPARQL query with decorator. So if you could try to think about like adding SPARQL Transformers still as a decorator in a way, so that you have this interesting syntax.
So all of the decorators are there. So all the part that in YAML, where you write in YAML in SPARQL queries, you have here in the Garlic object of a JSON query for SPARQL Transformer. So you will keep all the feature of the Garlic. Moreover, a thing that I can add is that in the same repository, you can mix SPARQL query and JSON query, and it's totally fine. Each query is handled as a single, so there is no conflict. Is this answering your question?
Yes, I think in part, yeah, thank you. Maybe I just missed a part. So you basically, you treat this this description, this SPARQL Transformer description as one of the things that grlc can basically digest and add to the endpoint. No?
Yes.
Yes, exactly. That's what it is.
Okay.
Yeah, if you think basically if the file is a .rq, it's treated as a SPARQL query. If the query is a JSON, if it is that JSON is treated as a JSON query. So it's fully automatic.
Great, thank you.
Okay, if there are no more questions, I think we can close here. Again, feel free to write to us anything about the tutorial, about grlc, about SPARQL Transformer, about any other thing that we have seen together today. We'll be very happy to answer you. Open issue on the GitHub repositories if you want, if you find any problems.
Yeah.
And we really thank you. Really thank you to have been with us today. And you want to say anything else, Albert?
No, nothing else to add. Just
okay.
Thank you all for being today here, and enjoy the rest of the conference.
Indeed. Thank you. See you soon, possibly physically in the future. Ciao.
Ciao. Bye-bye.
There is a question about a Slack channel for this tutorial conference where recording will be shared. We will share at a certain point on our website, on the website of the tutorial. So there will be some links to a video. Okay. Okay.